Good afternoon, students. This is Arvind, Assistant Professor, Department of Discipline, DBS Economy. So, in the previous classes, I discussed about methods of controllable value generation. Okay, like TSC, TCR, or FC, TCR, TSC, and TCR, like that we have discussed. And from onwards, I am going to discuss switching type lag compensator. Switching type lag compensator. Okay. So firstly, I will discuss this switching type converter type lag generators. So after we discussed static lag generators in the previous session, that will use the static lag generators generate or observe the controllable reactive power, that is that. Okay, static lag generators generate or observe controllable reactive power, that one is called that, by synchronously switching capacitor and reactor banks in and out of the network. So the aim of this approach is to produce a variable reactive shunt impedance that can be adjusted or in a step like to meet the composition requirements of the transmission network. So the aim of this approach is to produce a variable reactive shunt impedance that can be adjusted to meet the compensation requirements of the transmission network, and possible way of generating controllable reactive power directly. Without the use of AC capacitors or reactors. So in this switching converter generators, I am not going to use the capacitors or reactors, and I am going to generate the controllable reactive power directly by linear switching power converters. So it was disclosed by B.Tech-I in 1976. So this concept was introduced by B.Tech-I in 1976. Okay. So these converters means DC to AC or AC to AC converters. Okay, these converters are operated as voltage and current sources, and they provide reactive power essentially without reactive energy storage components. Okay, by circulating alternating current among the phases of the AC system. Okay, in this one I am taking the converters. These are operated as voltage and current sources, and these are used to produce reactive power. Okay, essentially without reactive energy storage components, that is capacitor and inductor. Okay, by circulating the alternating current among the phases of the AC system. And functionally, from the standpoint of reactive power generation, okay, their operation is similar to that of an ideal synchronous machine, okay, whose reactive power output is varied by excitation control. This is for functional. So from the standpoint of reactive power generation, their operation is similar to that of the ideal synchronous machine, that means whose reactive power output is varied by excitation control. So like the mechanically powered machine, they can also exchange real power to the AC system if supplied from an appropriate, usually DC energy source. So because of these similarities, with a rotating synchronous generator, they are termed static synchronous generators. Okay, because of these similarities, with a rotating synchronous generator, they are termed this one as static synchronous generator. Shortcut we will call it as SSGs. Static synchronous generators. Okay. Next. So when an SSG is operated without an energy source, and with appropriate control to function as a shunt-connected reactive compensator, it is termed analogously to the rotating synchronous compensator, that is condenser, and a static synchronous compensator, StatCom. Rotating synchronous compensator is nothing but condenser, and a static synchronous compensator, that is called as condenser or StatCom. Okay. So here the controllable reactive power can be generated by all types of DC to AC and AC to AC switching converters. Controllable reactive power can be generated by all types of DC to AC and DC to AC to AC switching converters. So the former group is generally called DC to AC converters. That is previous one. Okay, the former group is generally called DC to AC converters or just converters, whereas The latter one is referred to as frequency changers or frequency converters or cycloconverters. Okay, the latter one is referred to as frequency changers or frequency converters or cycloconverters. So the normal function of converters is to change DC power to AC, and that of frequency changers to change AC power from frequency to AC power of under frequency. Okay. Next, so here I am considering a power converter of either type consists of an array of solid state switches which connect the input terminals to the output terminal. So here I am considering a power converter of either type. It consists of an array of solid state devices which connect the input terminals to the output terminals, and consequently a switching power converter has no internal energy storage, and therefore the instantaneous input power must be equal to the instantaneous output power. Okay, because switching power converter has no internal energy storage. That's why the instantaneous input power must be equal to the instantaneous output power. So in the case of DC to AC converters, so for suppose I am taking the DC to AC converters case, in that one the DC terminals are usually considered as input. The DC terminals are usually considered as input, and therefore voltage source and current source converters are distinguished accordingly to whether these are shunted by voltage source or by current source. Here in this one the voltage source acts as a capacitor and current source acts as an inductor. Okay, and due to their practical importance in transmission applications, voltage source and current source converters are treated in detail to provide the necessary technical foundation for the use in practice controllers. Okay, due to the practical importance in transmission applications, voltage sources and current source converters are treated in detail to provide necessary technical foundation for the use in practice controllers. So converters presently employed in practice controllers are the voltage source type, but current source type converters may also be used in the future, but at present we are using the voltage source type. Okay, voltage source type converters we are using. Okay, so the major reasons for the prevalence of the voltage source converters are: first one is current source converters require power semiconductors with bidirectional voltage blocking capability. So the available high power semiconductors with gate turn-off capability, that is GTO and IGBT, say that cannot block reverse voltage at all or can only do it. They cannot block reverse voltage at all or can only do it. So with the determinantal effect on other important parameters, that is increased conduction losses. Okay, coming to the second one, practical current source termination of the converter DC terminals by a current charged reactor is much losser than complementary voltage source termination by a voltage charged capacitor. This is the one of the major reasons why we have preferred over the current source converters. Okay. Next, coming to the third one, the current source converter requires a voltage source termination at AC terminal. The current source converter requires a voltage source termination at AC terminal, usually in the form of capacitor filter. And the voltage source converter requires a current source termination at the AC terminal that is naturally provided by the leakage inductance of the coupling transformer. And coming to the fourth reason that is the voltage source termination tends to provide an automatic protection of the power semiconductor against transmission line voltage transients. Okay, in this one the current source converters may require additional lower voltage protection or higher voltage rating for the semiconductors. Okay. So however, the current source converters have one major advantage over their voltage source counterparts in that they are almost totally immune to terminal shorts due to their inherent output current limitation provided by the DC current source. So because of these practical advantages, voltage source converters offers in this all other chapters dealing with practice controllers also, only this type of converter is considered, that is voltage source converters, and treated only to the extent necessary to convey the operating principles and characteristics of the particular controllers discussed. Okay, we are going to discuss operating principles and some characteristics of this particular controller. Okay, however, the operating principles and characteristics of the controllers discussed would generally remain valid if the future implementation would be based upon transfer converters. That is discussed in the chapter 4, that is transfer converter concept. Okay. Next, coming to the basic operating principles in the switching converter type latch generators. Okay, so the basic principle of reactive power generation by a voltage converter is akin to that of the conventional rotating synchronous machine shown schematically in the diagram. That is, this is the diagram. This is used for the reactive power generation by a rotating synchronous compensator. Okay, it is also called as condenser. Okay, so the basic principle of the reactive power generation by a voltage converter is similar to that of the conventional rotating synchronous machine. This is a diagram. So in this diagram we have the system bus, and the system bus consists of coupling transformer and some reactances and leakage inductance, and we have the generated EMF and one exciter. Okay, so for purely reactive power flow, the three-phase induced electromotive forces, that is EMF, that is EA, EB and EC of the synchronous rotating machine are in phase with the system voltages, that is VA, VB and VC for purely reactive power flow. Okay, the EMF is in phase with the system voltages, and the reactive current I drawn by the synchronous compensator is determined by the magnitude of the system voltage V. Okay, the reactive current I drawn by the synchronous compensator is determined by the magnitude of the system voltage V, that of the internal voltage E, and the total current reactance X. Okay, and next we have the equation for this one. I is equal to V minus E by X. So the corresponding reactive power Q exchanged can be expressed as follows. So here I am taking the expression for the reactive power exchange, that is Q is equal to 1 minus E by V by X into V square. So by controlling the excitation of the machine and hence the amplitude V of its internal voltage relative to the amplitude V of the system voltage, the reactive power flow can be controlled. By controlling the excitation, we have to control the reactive power flow. Okay, so increasing E above V. So if we increase the E above V, results in a leading current. That is, the machine is seen as a capacitor by the AC system. Results in a leading current, that is, the machine is seen as a capacitor by the AC system. And decreasing E below V, that produces a lagging current, that is, the machine is seen as a reactor or inductor by the AC system. The two cases, below E above V and E below V. So under either operating condition, a small amount of real power of force flows from the AC system to the machine because to supply its mechanical and electrical losses. To supply the electrical and mechanical losses, the small amount of real power flows from the AC system to the machine. From the AC system to the machine. So note that if the excitation of the machine is controlled, okay. So if the excitation of the machine is controlled, so that the corresponding reactive output maintains or varies a specific parameter of the AC system, that is bus voltage, and then the machine function as a rotating synchronous compensator, that is condenser. Okay, and the basic voltage source converter scheme for reactive power generation for this purpose is shown schematically in the form of a single line diagram. I will show you one single line diagram that uses a basic voltage converter scheme for reactive power generation. So this is the diagrammatic representation of this one. So here also I am taking the same system bus V and coupling transformer and a transformer leakage reactance X, but here I am taking DC to AC switching converter with a voltage source converter VDC. Okay, here I am taking a switching converter, that is DC to AC. Okay, this is the reactive power generation by rotating a voltage source switching converter. Okay, so from a DC input voltage source provided by the charging capacitor CS. So this one CS, VDC CS. Okay, from a DC input voltage source provided by a charging capacitor CS, the converter produces a set of controllable three-phase output voltages. The converter produces a set of controllable three-phase output voltages with the frequency of the AC power system. Okay. So here each output voltage is in phase with and coupled to the corresponding AC system voltage via a relatively small tie reactance. Okay. That is in between 0.1 to 0.15 per unit. Okay. Each output voltage is in phase with the AC system voltage through the coupling. That is the coupling transformer. Okay. This is the diagram representation of that one. And next, so by varying the amplitude of the output voltages produced, the reactive power exchange between the converter and the AC system can be controlled in a manner similar to that of the rotating synchronous machine. So that is, if the amplitude of the output voltage is increased, okay, the amplitude of the output voltage is increased above that of the AC system voltage, then the current flows through the tie reactance from the converter to the AC system. Okay, and the converter generates reactive power for the AC system. The converter generates reactive power for the AC system. And if the amplitude of the output voltage is decreased below the AC system, then the reactive current flows from the AC system to the converter, and the converter absorbs reactive power. So in the previous case, it generates reactive power for the AC system, and in the second case, the converter absorbs reactive power. That is for the capacitor, and this is for the inductive. Okay. Next. So if the amplitude of the output voltage is equal to the AC system voltage, so greater than, less than, and equal to, the reactive power exchanges is 0. Okay. So the three-phase output voltage generated by a voltage source DC to AC converter operated from an energy storage capacitor. So in the diagram I already shown that one. So the voltage source converter, that is nothing but a DC to AC converter, is connected to the voltage source converter which acts as a storage capacitor in this one. So all of the practical converters so far employed in actual transmission applications are composed of a number of elementary converters, that is of single phase H bridges or three phase 2-level 6-pulse bridges or three phase 3-level 12-pulse bridges. I will show this diagram. Combination of these. This is the diagram. On the left side we have the single phase 2-level H bridge. Towards the right we have 3-phase 2-level 6-pulse bridge, and to the right we have 3-phase 3-level 12-pulse bridge. So this is the basic converter schemes used for the reactive power generation. So here we have single phase, that is VOA. Okay. So here we consist of the thyristor valves, the combination of diodes. Okay, and one capacitor. And in the three-phase we have three valves, all consist of the combination of thyristor and diode, and these are consist of one capacitor and three phases. This is three-phase 2-level 6-pulse bridge. And coming to the third one, that is three-phase 3-level 12-pulse bridge. So here we have 3-level 12-pulse bridge. So here we consist of how much? Six valves. That means 6 thyristor valves. So it is a combination of thyristor and diode. And it consists of two capacitors, C by and C by, and we have three phases, VA, VB, that is VOA, VOB, and VOC. Like that. These are used for the basic converter schemes used for the reactive power generation. Okay. Next, the valves used in the elementary converters usually consist a number that is 3 to 10 of series connected power semiconductors, that is GTO thyristors, with reverse parallel diodes. So already I discussed that one. Okay. The valves used in elementary converters usually consist of series connected power semiconductors, that is GTO thyristors, with reverse parallel diodes. And each elementary converter, as discussed in the voltage source converter concept, produces a square or quasi square or a pulse width modulated output voltage waveform. Okay. So these component voltage waveforms are phase shifted from each other and then combined usually with the use of appropriate magnetic components, okay, to produce the final output voltage of the total converter. Okay, that's why we are considering these things. Okay, so with sufficient design, this final output voltage can be made to approximate a sine wave closely enough so that no filtering is required. So if you get a pure sine wave, there is no filtering is required. So for example, I will show the diagram. It will show a typical 48 pulse output voltage waveform generated by the combined output of either 8 to level 6 pulse or 4 3-level 4 pulse converter. So 8 into 2 6 pulse, 8 2 level 6 pulse, that is 6 into 8, that is 48, and 12 into 4, that is 48. So I will show the diagram, this one. Okay, typical output voltage and current waveforms of a 48 pulse generator generating reactive power. So here I am taking the time and the current. Okay, here we have the step-by-step manner of the sine waves. Here we have the 2 sine waves, and for the sine wave we have the step-by-step, that means Price's square wave. So this pure sine wave is for the line voltage, and this Price's sine wave is for the output voltage, and this sine wave is for the output current from one to from this one. This is the 48 pulse converter generating reactive power operation for the output voltage waveforms. So in this and subsequent fact controller chapters, the waveform construction aspects of the converter will not be any further discussed. Okay. So and the term converter here on will imply a complete converter structure capable of producing a substantially harmonic free output voltage. Okay, substantially a harmonic free output voltage. And next, so the operation of the voltage source converter used as a controllable static wire generator, okay, can be explained without considering the detailed operation of the converter valve for basic physical laws governing the relationship between the output and input port. By using these basic physical laws, we are going to explain the operation of the voltage source converter, that too as a static wire generator. Okay, without considering the detailed operation of these things. And the key to this explanation resides in the physical fact that, like in all switching power converters, the next instantaneous power at the AC output terminals must be always equal to the net instantaneous power at the DC input terminals. I already discussed these things in the earlier slides. Okay. So, since the converter supplies only reactive output power, okay, the real input power provided by the DC source. Okay, the converter supplies only reactive output power, then the real input power provided by the DC source. Okay, so furthermore, since reactive power at zero frequency by definition is zero, the DC capacitor plays no part in the reactive power generation. Okay, so in other words, the converter simply interconnects the 3 AC terminals in such a way that the reactive output currents can flow freely between them, because of the interconnection. So viewing this from the terminals of the AC system, one could say that the converter establishes a circulating current flow among the phases with zero net instantaneous power exchange. Okay, and the need for the DC storage capacitor is theoretically due to the above stipulated equality of the instantaneous output and input powers. So the need for the DC storage capacitor is theoretically due to the above stipulated equality of the instantaneous output and input powers. So the output voltage waveform of the DC to AC converter is not a perfect sine wave. Okay, the output voltage waveform of the DC to AC converter is not a perfect sine wave. So for this reason, the net instantaneous output power VA has a fluctuating component even if the converter output currents were pure sine waves. Okay, for this reason, what reason? The output voltage waveform of the DC to AC converter is not a perfect sine wave. For this reason, the net instantaneous output power has a fluctuating component even if the converter output currents were pure sine waves. So that's why, in order to violate the equality of instantaneous output and input powers, the converter must draw a fluctuating, that is ripple. fluctuating current or ripple current from the DC storage capacitor. Okay, that provides a constant voltage termination at the input. That provides a constant voltage termination at the input. And the presence of the input ripple current components is thus entirely due to the ripple components of the output voltage. Okay, which are a function of the output waveform fabrication method used. Okay, next in a practical VAR generator, as explained earlier, the elementary 2 or 3 level converters would not meet practical harmonic requirements either for the output voltage or for the input current. Okay, in a practical VAR generator, the elementary 2 or 3 level converters, already discussed of this 2 level or 3 level converters, would not meet practical harmonic requirements either for the output voltage or for the input current. So, however, by combining a number of these basic converters into a multi-phase structure, the output voltage distortion and capacitor ripple current can be theoretically reduced to any desired degree. Thus, a static VAR generator employing a perfect voltage source converter would produce sinusoidal output voltages, would draw sinusoidal reactive current from the AC system and zero input current from the DC capacitor. Like that, we will form the waveforms, pure sine waves. Okay. Next, so in practice, due to the system unbalance and other imperfections, as well as economic restrictions, these ideal conditions are not achieved, but can be approximated quite satisfactorily by appropriate converter structures and wave shaping techniques, so that the size of the DC capacitor in normal transmission applications remains relatively small. Okay, and in a practical converter, the semiconductor switches are not lossless. Okay, in a practical converter, the semiconductor switches are not lossless, and therefore the energy stored in the DC capacitor would be used up by the internal losses. Okay, in a practical converter, the semiconductor switches, remember GTO thyristors, are not lossless, and therefore the energy stored in the DC capacitor would be used up by the internal losses. So the DC capacitor is nothing but the voltage source converter in this case. So however, these losses can be supplied from the AC system by making the output voltages of the converter lag the AC system voltages by a small angle. So in this way, the converter absorbs small amount of real power from the AC system to replenish its internal losses and keep the capacitor voltage at the desired level. Okay, so the mechanism of phase angle adjustment can also be used to control the VAR generation or absorption by increasing or decreasing the capacitor voltage, and thereby the amplitude of the output voltage produced by the converter. Okay. So the DC capacitor also have a vital function, that is, even in the case of a perfect converter, in establishing the necessary energy balance between the input and output during the dynamic changes of the VAR output. Okay, so it is of course also possible to equip the converter with a DC source, that is battery, or with an energy storage device of significant capacity, that is large DC capacitor or superconducting magnet. So in this case, the converter can control both reactive and real power exchange with the AC system, and thus it can function as a static synchronous generator. Okay, so from this one, the capability of controlling real as well as reactive power exchange is a significant feature which can be used effectively in applications requiring power oscillation damping, leveling peak power demand, and providing uninterrupted power for critical loads. Okay, and this capability is unique to the switching converter type VAR generator, and it fundamentally distinguishes it from its conventional thyristor controlled counterpart. Okay, this is the basic operating principle for the switching converter VAR generator, and in the next class I am going to discuss basic approaches for this system. Okay, for this concept. Okay, thank you for watching this video.